Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Welcome back to our Deep Learning course. Today, we're continuing Chapter 5, Classic Convolutional Neural Networks 4. Our focus is Part 5.4, Batch Normalization Techniques, a key optimization method that makes deep network training easier. Let us start with the core idea of batch normalization, then apply it to a cat and dog classification task. First, let us clarify two key concepts. First, batch. When updating model weights via backpropagation, we don't use all training samples, we only use a small portion. This small portion is called a batch or mini-batch. Second core idea of batch normalization, as the slide S diagram and text explain, during neural network training, we don't feed the entire input dataset at once. Instead, we randomly split the input into several equal-sized blocks, each is a batch. A complete epoch training round means training through all these batches once. Batch normalization adjusts the data distribution of each batch to make training more stable and faster. We'll see how it works in the case later. To practice batch normalization, we'll use a cat and dog image classification task. First, we prepare data with Keras image data generator, just like before. Set im size equals 128. We'll resize all images to 128 multiplied by 128 for consistency. Training generator reads from /data_bn or catdog, or train, normalizes pixels to 0 to 1, rescale equals 1/255, uses batch size 200 and class mode equals categorical, 1 hot labels for cat or dog. Validation generator reads from /data_bn or catdog or validation with the same settings. This generator lets us handle large cat-dog datasets without loading all images into memory, perfect for practical tasks. Next, we visualize 10 sample images to confirm the data generator works. The code is straightforward. First, get one batch of data from the generator we'll use. Next, validation underline generator to get X equals images, Y equals labels. Second, create a 2-row 5-column figure with matpletives, set height 6, width 15 for clear display. Third, flatten the axes and loop through 10 images AXI. ImShowXI displays each image. The slide shows the result. You can clearly tell which are cats and which are dogs. This confirms the generator is reading the correct data, so we're ready to build the model with batch normalization. Now let us build a logistic regression model with batch normalization (BN) using Keras. Let's walk through the code step by step. First, input layer, input im size 3 accepts 128 multiplied by 128 color images, cat or dog are color images. Second batch, normalization layer, X equals batch normalization X. This is the key layer. It normalizes the input data of the next layer, stabilizing training. Third, flatten layer, X equals flatten X, converts the 3D image tensor 128 multiplied by 128 multiplied by 3 into a 1D vector. 128 multiplied by 128 multiplied by 3 equals 49,152 elements. Fourth, output layer X equals dense2, activation equals softmax X, 2 units for cat or dog classification. Softmax outputs probabilities. Finally, Model 1 summary prints the model structure. We'll analyze this structure next. Let us analyze the model structure from the summary output. This helps us understand how batch normalization adds parameters. Input layer. Input 1 has shape none. 128, free, 0 parameters as expected. Batch normalization layer batch normalization 1, has 12 parameters. Y, for each input channel, 3 channels total Bn has 4 parameters, gamma, beta, moving mean, moving variance 3, multiplied by 4, equals 12. Among these 6 are trainable gamma and beta, which adjust the normalized data, and 6 are non-trainable, moving mean and variance updated during training. Flatten layer, flatten 1 has 0 parameters, only reshapes data. Dense layer, dense 1, has 98,306 parameters, 49,152, multiplied by 2, plus 2 biases. Total params are 98,318. Most come from the fully connected layer, while Bn adds only a small number of parameters. Next, we compile and train the model with Bn. Compile use, model 1, compile optimizer, equals, atom LR, equals, 0.01, loss, equals categorical underline, cross entropy metrics equals accuracy atom optimizer with learning rate, 0.01, Bn, lets us use a slightly larger learning rate, categorical underline, cross entropy for binary classification, with 1 hot labels and track accuracy. Train use, model 1, fit underline generator, train underline generator epochs equals 200 validation, underline data equals validation underline generator train, for 200 epochs, Bn, speeds up convergence so 200 epochs are manageable and validate on the test set to check generalization. With Bn, the model should train more stably than the model. Without Bn, you'll notice less fluctuation in training or validation accuracy. Now let us look at the 8th slide, which is still part of 5.42, logistic regression, with Bn. Here, we'll discuss how to extend the logistic regression model with convolutional and pooling operations. First, the slide mentions a wide model. This type of model uses many convolution kernels, meaning it has deep convolution channels to extract rich features. Then, regarding the code, it's similar to the logistic regression code we covered earlier in section 5.42, but with 2 key additions. A convolution operation we use 100 convolution kernels of size 2 multiplied by, and the second convolution kernel uses valid convolution, which means no zero padding, so the output size reduces based on the kernel's dimensions. A pooling operation we perform max pooling with a target size of 16 multiplied by 16. This step reduces the spatial dimensions of the feature maps, making the model more efficient and better at capturing key patterns. These additions transform our basic logistic regression into a model with CNN-like components, convolution, and pooling, helping extract more powerful image features for classification. Let us wrap up with key takeaways about batch normalization. Model adjustment. In our example, we didn't use convolution kernels. Instead, we added a Bn layer to a simple logistic regression model. This shows Bn can be used in different model structures, not just deep CNNs. Bn's role. Batch normalization is incredibly helpful in many scenarios, for example speeding up training, reducing overfitting, allowing larger learning rates. But it is not a one-size-fits-all solution. There are cases where it doesn't improve results. Exactly when Bn works best is still a topic that needs deeper research. Keynote: Bn adds a small number of parameters but brings significant benefits. This is why it's widely used in modern deep learning models. Remember, Bn is a tool. Test it in your task to see if it helps.